All right, so now we get to my favorite part of every chapter, which is talking about the reactions that these functional groups undergo. One thing I do want to point out is that is very much so how things are kind of organized in organic chemistry. We think of, for example, alcohols as undergoing certain types of reactions, which is different from, say, ethers and the type of reactions that they undergo. There may be some overlap, but generally speaking, we like to think about things. We like to reduce a molecule to its functional group and talk about the reactions that those particular functional groups undergo. So this one we've actually seen before, and this is a combustion reaction. Both alcohols and ethers can combust, meaning that we have our alcohol reacting with oxygen gas to produce carbon dioxide and H2O. Again, ethers, this could be an ether as well. Both of these are flammable, i.e. combustible, because you have an oxygen as part of your fuel source. It makes these a little bit tougher to balance, right? Before we said, save this guy to the end, and you still actually are going to do that same strategy. But nonetheless, when you're accounting for oxygens over here, you also need to account for the OH group, right? Because somebody, the carbon dioxide or the water, probably the water, but it doesn't really matter who, is going to end up getting the oxygen that was once in that alcohol group. So this just makes them a little bit tougher to balance. That's part of what you're going to be practicing. But yeah, they same reaction as we've seen. And if you've ever seen a chef do like a flambe or whatever, that's exactly the reaction that you're observing there. Okay. Alcohols also undergo dehydrations, okay, where they lose water. So let's just this is an example of a dehydration reaction. It's the exact opposite of the hydration reaction we learned about when we were talking about alkenes. So these can go either way. You can either make an alcohol from an alkene, or you can make an alkene from an alcohol, right? You can go either direction here. And let's just sort of note what's happening. I have my alcohol, the hydroxyl group on one carbon, and the hydrogen on the neighboring carbon will come together, come off as water, and that will allow those two carbons to now form a double bond. Right, so this is the opposite of an addition reaction. This is what we called our addition reaction, also called a hydration. Now we're talking about going the other way, a dehydration, where water is leaving and we're being left with a double bond. Okay. I think the most important thing about these dehydration reactions are, again, they have like a preference as to whether or not they want to go to a more highly substituted carbon or a less highly substituted carbon. The major product is the one that's formed by removing the hydrogen from the carbon atom that has a smaller number of hydrogen atoms. That's a really wordy way of saying the more highly substituted carbon. So let's look at an example here. Here we have, let's see, 1, 2, 3, 4, 5. So what would this one be called? We have 2-pentanol. Okay. And notice that if we were doing the dehydration, we could do it in, potentially we would have two different dehydration products. One where the double bond is formed with this N carbon here. So that would be CH2 double bonded CH, CH2, CH2, CH3, or, right, and so that's this carbon, or we could have where it bonds to this adjacent carbon, and so that would be CH3, CH, CH, CH2, CH3. Okay, so again, it's like the OH group is coming off, and that pair of electrons can go to either neighboring carbon. But one of these is the major product, and one of them is a very minor product. Okay, so again, The more highly substituted carbon gets the double bond. And again, by more highly substituted, I mean the carbon that has more carbon neighbors. So my green carbon has 1, 2 carbon neighbors. I guess I can do this in green. 1, 2 neighbors. My blue carbon only has 1 carbon neighbor. So the green carbon is the more highly substituted carbon. So this will be our major product. This is the minor product, okay? We're gonna focus on what is the major product for the most part, okay? Anyways, you're gonna have to know that there's this sort of preference as to where your double bond goes. Something very similar to what we saw when we were talking about the hydration reactions. There was a preference for where the OH group went. Here, there's a preference for which carbon gets the double bond. Okay, so yes, this would be the major product. And again, that double bond is going to form between the carbon that originally contained the hydroxyl group and the more highly substituted neighbor. Okay. So now let's talk about oxidation reactions and reduction reactions. So these are exactly inverses. Okay, so the opposite of oxidation is reduction. You may have in Chem3BF had to learn some complicated rules for if an element is being oxidized. The great news in organic chemistry, it very simply equates to the number of carbon and oxygen bonds. So if you oxidize something, you're increasing the number of carbon oxygen bonds. And if you reduce something, you're decreasing the number of carbon oxygen bonds. Okay. So let's take a look at primary alcohols first. Remember, those are alcohols where the carbon that they're bound to is only bound to 1 other carbon. So if I oxidize this compound here, I'm going to create more carbon-oxygen bonds. So what that's going to look like is this here. Right? I've now created a double bond between carbon and oxygen. Notice that I would have had to have lost 2 hydrogens in this process, this oxidation as well. One that was originally on the oxygen and one that was originally on the carbon. But I go from having 1 carbon-oxygen bond to 2 carbon-oxygen bonds. That's an oxidation. If I go the reverse direction, that's a reduction. This functional group here, where you have a carbon double bonded to an oxygen and that carbon's attached to a hydrogen, this is what's called an aldehyde. We're actually going to practice all the different functional groups in lab this week, but yes. Okay, aldehydes can be further oxidized. And what am I doing when I'm oxidizing? I'm just going to add another carbon-oxygen bond to that same carbon. And so in this case, that would be putting another OH group on there, right? So I'm replacing the hydrogen with an OH. This is what we call a carboxylic acid. Okay. Importantly, though, when I'm oxidizing, I'm increasing the number of carbon-oxygen bonds on this same carbon, right? So I go from 1 in my primary alcohol, 2 in my aldehyde, to 3 in my carboxylic acid. If I have a secondary alcohol, again, when I oxidize, I'm increasing the number of carbon-oxygen bonds. So again, I'm going to create a carbon-oxygen double bond, right? So I'm going from 1 to 2 on that same carbon. This functional group where I have an oxygen double bound to a carbon, but now that's bound to another carbon, not a hydrogen, this is what's called a ketone. So aldehydes and ketones are very similar. With an aldehyde, though, that carbon is necessarily bound to a hydrogen. Ketones cannot be further oxidized. Okay, you would have to break a carbon-carbon bond to do that. That's not what we're talking about. Okay, so again, primary alcohols can be oxidized twice. The first time to an alcohol or to an aldehyde. So I go from having one bond, oxygen-carbon bond to 2 oxygen-carbon bonds. They can further be oxidized a second time, where I've gone from 2 carbon-oxygen bonds to 3, adding another OH group. And again, that'd be going from an aldehyde to a carboxylic acid. Secondary alcohols can only be oxidized once. You can only go from an alcohol to a ketone, where I have my 1 bond to oxygen going from 2. I can't further oxidize this without breaking a carbon-carbon bond. So then if we have tertiary alcohols, these cannot be oxidized at all, right? Because we'd have to break one of these carbon-carbon bonds in order to form a double bond here. And that's just not what oxidation is. You can break carbon-hydrogen bonds, but you can't break carbon-carbon bonds when you're oxidizing. So this would be no product formation. Okay, we talked about methanol and how it was very toxic. That's because how the body gets rid of alcohols is by oxidizing them. And when you oxidize methanol or methyl alcohol, you get what's called formaldehyde, which is toxic. That's what they use to preserve dead bodies, actually, as well as formic acid, which is also toxic. Okay, both of these are very toxic. I think formaldehyde in particular makes you blind. So that's what you hear with methanol poisoning, is people actually go blind. Ethanol, the body actually gets rid of it the same way, but the products that are formed aren't quite as toxic. Okay, so ethanol can be oxidized to ethanal, so going from carbon-oxygen 1 bond to our double bond here. Ethanal is not great for you. Your liver is not very happy about it, but it's not as toxic as formaldehyde. Eventually, it'll actually be, I'm going to say it's kind of an oxidation, but this is with help of enzymes in your body. Eventually, we'll convert it all the way to CO2, and that's how it gets rid of it. But again, as it's going, it has this alcohol in your system, gets converted to an aldehyde and then to a carboxylic acid. The reason that heavy drinking is so bad for you is the accumulation of those aldehydes and carboxylic acids in the liver. Okay. Yeah, I mean, these are just blood alcohol levels with drinks consumed. I'm sure you guys will, be able to socially come up with your own responsible drinking. The bottom line is, after you get to like past 4 drinks, you're consuming what would be considered to your cells a toxic level of alcohol. Okay, and then lastly, we talk about oxidation with sulfur, with thiols as well, but it's a little bit different of a process. It's still called oxidation, but I want you to have these in 2 different places in your mind. Oxidation of alcohols is creating more carbon-oxygen bonds within a compound. When we're talking about the oxidation of thiols, we actually produce what's called a disulfide. So that is, we take 2 different thiol groups. There's one on this molecule, one on this molecule, and then we link them together. So notice that we've created now this carbon-sulfur-sulfur carbon bond. Okay, this is a form of oxidation. It's a little bit different. The reason that we're going to learn about it here, but especially when we talk about biochemistry, is because it's a really popular reaction for amino acids within proteins. So one of your amino acids within your body, cysteine, undergoes these types of reactions a lot. Okay, so now let's do some practice. Oxidation of this particular alcohol, what's the product going to be? All right, so first of all, notice that this is a secondary alcohol. So When I'm oxidizing, what I'm going to do is kind of how you can think about it actually is get rid of a hydrogen here, get rid of a hydrogen here, and form a carbon-oxygen double bond. So B would be the correct answer here. If instead the problem had asked not for the oxidation product, but let's do another kind of similar product where instead I wanted the dehydration product, what would that be? Right, for these dehydration reactions, that's when we are creating a carbon-carbon double bond. So that would be that there, okay. All right, and now lastly, we have a primary alcohol, and we want to know there are two different oxidation steps. So this will be problem 1, and this would be problem 2. What are the products after each step? Again, for that first one, we're just going to erase a hydrogen on the oxygen and a hydrogen on the carbon and create a carbon-oxygen double bond. So in this case, the aldehyde in C would be the product of step 1. And then when we go all the way to step 2, now we're creating yet another carbon-oxygen bond on this carbon, but we do that by introducing another OH group. So this would be the product of the second oxidation step.